Okay, for this section we need to distinguish between the energy of a body at rest and the total energy that it has when it moves. So when an object is at rest, its rest energy is equal to m naught c squared. Its rest mass times the speed of light squared. When it is moving, the energy is equal to m naught c squared, which is its original energy, plus the kinetic energy that it has. Now, E is equal to mc squared is the energy that it has plus the relativistic mass, because the mass is greater since the mass is moving. M naught is moving. So we can say that this, which is a relativistic energy, is equal to all of this. We also know that m is equal to gamma, the Lorentz factor, times by m naught. So the actual relativistic mass will be greater than the rest mass. Since m is the m that goes here, it's gamma m naught times by c squared. So this mass is multiplied by a factor of gamma here, and this will be the total energy. But in gamma, of course, you have the value for V. In the syllabus, they want you to do this particular kind of calculation, which is to determine the total energy of an accelerated particle. They've asked you specifically to do this calculation, so you should learn how to do this. Let's say we have an electron, which has a mass of 9.1 times 10 to the negative 31 kilograms, and it's accelerated through 1 million volts. This is going to give it a relativistic speed. If you calculate this as being half mv squared, you're going to find a velocity which is greater than the speed of light. So this cannot work. So we have to use the relativistic equations of mass and energy to be able to find precisely or exactly what this should be. So let's find its kinetic energy alone from its potential difference, where it's basically the charge times by the potential difference, E times V. The E is going to be equal to the charge on an electron, V is equal to the voltage, the potential difference, which is 1 million. So we have 1 million times by the charge on an electron, 1.6 times 10 to the minus 19. Now we know the total energy is equal to the rest mass energy plus the kinetic energy that we give it. How do we find the rest mass energy? Well, we know what the rest mass is, so we just have to convert it into energy. E is equal to mc squared. So this is equal to m naught, this is rest mass, c squared, plus the kinetic energy, which we've calculated here. You put these values in, and we have 9.11 times 10 to the negative 31 times by c squared, remember that's times by 9 times 10 to the 16, plus 1.6 times 10 to the negative 13. And this gives a value for the total energy, which is equal to mc squared. M, of course, is the relativistic value for the mass. So, how do you find out the relativistic mass? Well, you know that the total energy, you find the value for this, you know that's equal to mc squared, you just divide by c squared and you find m. So, the kinetic energy here is the final value you should get here, so I want you to calculate that. The total energy here is equal to mc squared, which is equal to 2.42 times 10 to the negative 13 joules. And find the mass, and you'll find out a value which is 26.9 times 10 to the negative 31 kilograms. Now the original mass is, the rest mass is 9 times 10 to the 31 kilograms. The relativistic mass in this example is roughly 3 times that. So remember, in this case, 1 million volts is going to be roughly 3 times the relativistic mass. Now we're going to do the same calculation but looking at units. First we're going to look at the units and see how they work out. Now you remember that it was pretty weird to have energy in electron volts. Remember the potential difference is equal to energy per unit charge. So the energy is equal to the charge times by the potential difference. Remember, using Einstein's mass energy equation is going to give us another convenient unit which is a bit like the electron volts. Remember, E is equal to mc squared. So this EV is equal to the energy is equal to mc squared. We rearrange that to find the m. We have the E basically divided by c squared. So it's going to be EV divided by c squared. So in other words, the unit of mass is EV c to the minus 2. This is a valid unit of mass. Now let's look at that example that we had before. to make things easier, we've got the rest mass in MeV per c squared. So remember, we're accelerating the electron through 1 million volts. Find its kinetic energy. Well, that's easy. We're using these weird units. It's equal to eV. So it's going to be 1 MeV, because it's 1 million volts times by 1 electron, so 1 million electron volts. The total energy is equal to the rest mass energy plus the kinetic energy. The rest mass energy is the m0 c squared, which is E is equal to mc squared, plus this kinetic energy that we worked out just now. How do we find out E is equal to mc squared? We know the rest mass is 0.510 MeV per c squared. There we go. And then multiply by c squared. So these c squareds cancel out. So the energy, the rest mass energy, is equal to 0.510 should be MeV. Plus the kinetic energy. So we end up with a sum of energy of 1.510 MeV. Remember, the original mass or the rest mass is 0.510, and we've basically got a relativistic energy of 1.5, so it's basically roughly 3 times as much. And the same as before, these have to agree with the previous answer, where we did it in kilograms. So you have to find out the relativistic mass. Know that this total energy is equal to relativistic mass times c squared. Just divide by c squared, and it's this value. Divide by c squared. 1.510 MeV per c squared. So once you know this, you know that the rest mass is 0.510 MeV per c squared. We know that relativistic mass is 1.510 MeV per c squared. You find the ratio of these two, and you should use in the Lorentz factor, and you should find that the speed of this electron is 0.93 c. You could also try doing this with just the non-relativistic form of half mv squared, and you'll find a velocity which is somewhat faster than the speed of light, which doesn't work. So when we have voltages like 1 million volts, the electron's going to be basically going at a relativistic speed. If it's 1,000 volts, then it's not going to be really going nearly enough for the relativistic effects to be significant. So the total energy, mc squared, is equal to the rest mass energy, m0 c squared, plus the kinetic energy. We're going to rearrange that a little bit. Let's make the kinetic energy the subject, is equal to mc squared minus m0 c squared. Now we also know that the mass, the relativistic mass, is gamma times m0, so we can substitute that in there now. So we have gamma m0 times by c squared minus m0 c squared. There's a nice bit of factorising that can go on here. We can factorise basically m0 c squared, and we end up with gamma minus 1 lot of m0 c squared. This equation here, kinetic energy is equal to gamma minus 1 m0 c squared, is in the data booklet.